Hello, everyone. Thanks for joining the session, Accelerating VR Adoption Using 5G Edge Computing. My name is Saravanan Shanmugam. I am the lead solutions architect for AWS Wavelength. Let's get started. Let's look at a quick view of the agenda today. So we'll just do a quick overview of AWS Wavelength, a mobile edge computing platform, why we built it, what does Wavelength solve for our customers, and where does it sit in the mobile carriers network as of today. And a quick overview of VR Stack. How does VR Stack looks like? Why it is important as we dig deeper into other aspect of the session. I feel that a quick overview of VR Stack would be important for all the audience. CloudXR in AWS Wavelength, right? One of the important thing that is happening in the VR space is NVIDIA's CloudXR server and the client-side stack, and how we can deploy this. What are the learnings that we have done so far with respect to running CloudXR in AWS Wavelength, and how 5G can complement VR technology when it is running in the AWS Wavelength. That's the most important part of the presentation today, and all the learnings that we have taken so far, and all the sharings that I'm going to do today in this call. And finally, the most important thing is the results that we have seen. Where are the areas of improvement? What are the areas to actually dig deeper? And certainly work very closely with our partners like NVIDIA and our carrier partners, and help shape the industry towards VR acceleration using 5G and edge computing. And finally, we'll talk about some of the next steps and all the key things that we are going to do together with various customers and partners, and learning and accelerating the adoption in the space. All right, so let's actually, as I mentioned, let's actually do a quick overview on AWS Wavelength, right? Intentionally, I built this slide in such a way that there is a right and the left-hand side for this slide, right? So the right-hand side is obviously the mobile network, because we are talking about 5G and how to accelerate VR adoption in the 5G network. Let's take an example of how an application running in the region is accessed today from a mobile end user, right? So we have a mobile network on the right-hand side and a region, any region for that matter, right? We build regions as fast as possible. We have like 25 regions, plus we're building more to get closer to the customer, right? So when a customer chooses to deploy their application, the first thing that they do is they pick a region, they deploy their application either through EC2 containers or our own managed services, and expose these services to their end users. In this case, the end user is the mobile user. So how does the packet flow from a mobile user all the way to the application services which is running in the region? Typically, as you see, the packets flow through a radio network, a backhaul network, and a packet core, and then there is a data network, right? This is the standard practice around 3GPP on how the packet flows from a mobile network outside of the carrier network, and then the carrier routes the traffic using their peering exchanges with other carriers, and then finally the packet gets on to the internet, comes to Amazon backbone, and finally to the region, right? We know that this path is a best effort path, right? Most of the traffic flows through this path from a mobile end user application, right? When an application is running in the region. And so because of this, the end user experience is going to be, I wouldn't say it's going to be bad, but it's going to be dependent, very, very dependent on how this path performs. Sometimes it actually performs well, sometimes it's bad because of the best effort nature of this path. There's going to be packet loss, there's going to be variable jitter and latency, and it is, at the end of the day, it is going to affect the end user performance, right, or end user experience. What we have done is, working backwards from customer challenges, we have done a lot of innovation in the space on how can we solve this latency challenge for our customers, right? We have built individual services, we have untethered individual services from the region, like Lambda at the Edge, for example, CloudFront, Global Accelerator. All these are services which is running closer to the edge of the network in our own transit center or POP locations and things like that, right? So we're trying to get closer and closer to the customer so that we can reduce the need for number of hops and also increase the user experience. But this can be done only for certain applications, right? You can't just bring the entire workload and run closer to the edge by means of this individual services approach. And that's where Wavelength comes into the picture, right? Wavelength is a completely dramatically different thought process on how we are thinking about edge computing and how we can solve some of the customer challenges around low latency and high throughput applications, especially when with the advent of 5G and how 5G is going to bring in new radio technologies and how it is actually going to improve the throughput as well as the latency profile of how devices are accessing the networks. And more spectrum is added into the 5G NR specifications. So carriers are going to provide more options and more devices and more connectivity options with more bandwidth available, which is going to really trigger a flywheel type of an effect where more bandwidth is going to be, more applications are created and more data is going to be created. Do you really want to transport all this data across the backhaul into the internet and then all the way back to the region to process the data? So we need to think differently, and that's where wavelength kind of comes into the picture, where can we eliminate the need for sending those packets across the carrier backbone, internet, and Amazon backbone? Finally, it ends up in an application which is running in the region, right? And that's where wavelength dramatically changes, where we bring in our own infrastructure, like the AWS infrastructure, compute, storage, network, and then embed them inside the carrier's own data center and connect that back to our region, one of the primary regions, and using something called a service link, a high bandwidth link. And for our customers, at the end of the day, we expose the wavelength as if it's another availability zone for the customers so that they can go and extend their VPCs by means of simply creating a subnet in the wavelength zone. Right? I'll give you an example. Today, we have like 10 wavelength zone with Verizon, 2 with KDDI, 1 with SKT, and 2 coming with Vodafone in the UK and Germany. So what does it mean is for customers who wants to serve their mobile customers in Verizon networks or SKT, KDDI, and Vodafone, they now have a choice to deploy their workloads close enough to the mobile packet core and then serve their applications at close inside their mobile packet core, right sitting next to the packet core. That's what wavelength is about. Pretty simple concept, but a very powerful concept where AWS infrastructure is available at the edge of the mobile network. So a customer who is deploying an application, say for Boston Verizon customer, and they want to really serve them at a very low latency and high throughput because 5G is providing that level of connectivity, but you want the data to be processed as close as possible to the data source or to the customer using AWS services. That's where wavelength comes into the picture. For our customers, for our developers, for enterprises, for small businesses, whoever wants to get started with edge computing inside a wavelength using Verizon in US, all they have to do is simply get access to a wavelength zone and pick that wavelength zone, deploy a subnet, and get started. That's pretty much it is. It's just a couple of clicks and you get started. We also introduced this concept called carrier gateway, where the packets which is originating from the wavelength zone subnet can actually go in and out of the carrier networks without going back to the region and then getting routed through our backbone, right? That's the key part of the promise of low latency. We don't want this traffic to go back to the region for routing. So all the packets and all the application traffic which originates from the wavelength zone, which is targeted towards the mobile network, can seamlessly get routed and NATed by the carrier gateway. It is very similar to an internet gateway in the region, where it does the routing and NATing function. It exactly does the same thing in a wavelength zone. So now, if you overlay the 5G network or the radio network, is basically the radio network, backhaul, packet core, and then the data network. So we coexist, or we co-locate our wavelength zone right where the mobile packet core is happening, so that the packet doesn't have to traverse or doesn't have to exit the carrier network before it can land on an application, an EC2 application or a container application, which is running inside the wavelength zone for that customer. So technically speaking, if you have to distribute your workload across these 10 wavelength zone for Verizon's mobile customers, you basically go and deploy them. For KDDI customers, you pick the Seoul region and then you go and deploy your applications in the SKT wavelength zone. So that's how wavelength zone works. It's a logical extension of a region into a carrier network where you can deploy and get that low latency benefit for your customers. Pretty simple and very cool concept. All right, so let's keep the wavelength on one side of the puzzle, right? That's what mobile edge computing offers. We bring in an AWS infrastructure ready to go. But how does it affect the VR adoption, right? The topic today is how can I accelerate a VR adoption using a 5G network? Let's quickly look at a VR stack. How does a VR stack look like? Again, it's not a deep dive discussion about VR stack, but just to expose yourself to CloudXR, what CloudXR, NVIDIA's CloudXR brings to the table, and how can we use CloudXR to accelerate the adoption of VR using edge computing. So before we get there, let's quickly look at a VR stack, how it looks like. Pretty simple. Say you're playing a VR game like Beat Saber, right? I've been playing Beat Saber a lot because I'm doing a lot of testing on VR with 5G, and that's why I mentioned this name, a Beat Saber. You can actually, there's hundreds and hundreds of great games over there, but let's take VR Beat Saber as an example. So you have a VR app, you have a head mount device, and basically you have either a tethered or untethered, you have a runtime engine, and then the lens wrap and all the heuristic stuff that goes back and forth, right? This is a typical VR stack looks like, right? You have an application, the application wants to access your hardware, the hardware can be accessed by means of the runtime, and because of the runtime, it can access the hardware as well as the late and lens wrap and things like that. Pretty simple, right? The latency requirement, the throughput requirement between the compute and the application is so strict, right? In terms of low millisecond, right? Low millisecond. That is very important. And the throughput is also very important. We'll talk about that, how CloudXR and 5G can solve that problem. So the idea behind this is it's co-located, right? It's basically co-located. You can have a head mount device which has all the GPU compute embedded in the device, and then you run an application. Certainly that's the best experience you're going to get because there's not much of latency. The latency is basically the electrons moving across, the application of the rendering engine and then the circuitry board, right? That's the thing that we're looking at as far as a tethered or untethered type of an architecture, right? But let's look at CloudXR Stack, right? What does CloudXR Stack plays a role in the VR ecosystem? So again, let's disaggregate it a little bit, right? We have the application, the VR app with the OpenVR runtime, because these applications are built assuming that they can access the hardware going through the OpenVR runtime. On the other hand, you have the head mount device with the VR runtime and the lens wrap and all those external devices that you connect. So at the end of the day, the application has to be told how to access this hardware using a runtime. Guess what? The NVIDIA CloudXR Stack kind of bridges that together by means of connecting them remotely using an external network. So they come up with this virtual head mount driver, an audio driver, video encoder, audio encoder, etc., etc. And then on the other side, they use the decoder on the client side and build these SDKs on the server side as well as the client side. This is pretty cool, right? So where you're disaggregating the hardware and the app and making them talk with each other, assuming that they're all connected together using that abstraction layer. And that abstraction layer is the SDKs on the server side and the SDK on the client side. A lot of cool things happens. We will go a little bit deeper in the coming slides, but this is what at the end of the day, at the highest level, the CloudXR Stack does, right? If you kind of zoom in, what it actually does is it connects these devices, the head mount devices and the application using an external connectivity using 5G or Wi-Fi or Ethernet. But this talk is very specific about 5G, how we can leverage 5G and edge computing to make VR be very successful and be adopted by mass, right? That's the key part of this talk. And the most important thing, again, if you go deeper, is there are sessions that is established. When you actually do a VR session from your head mount device connected over a 5G network with the VR runtime and a client which is running, or a server which is running in an external network, the connectivity becomes such a key component. What type of protocols are used? What are the different packets that flows back and forth? And what are the things that developers and network providers and edge providers, like edge computing providers like us, have to be very cognizant of? There are compute requirements, there are head mount device requirements, there are 5G requirements. There's a lot more happening in this space, right? Our customers are challenged to make this successful for their end customer, and we are working backwards from our customers' challenge and see how we can work together to build this ecosystem and what we can bring to the table in terms of our understanding about edge computing, working with our carrier partners from a 5G network standpoint, and working with so many other providers like the device ecosystem providers, the SDK providers, and the application providers, right? A lot of things, a lot of moving parts when you want to do CloudXR or any type of VR over 5G, right? I'm focusing on CloudXR because we have done a lot of testing in this space. We are working with NVIDIA pretty closely on understanding, as well as other partners as well in this space, and understanding how their application behaves, what type of GPU is required on the edge, and what type of network requirements these applications have, and how can it be programmatically provided to this application when they are doing a VR session, remote VR session between a server and a client, right? That's pretty much the core part of this discussion is about. All right, let's move on. So how did we actually implement this in the lab? Because this talk is around testing, results, next steps, and what we have learned so far, and what are the things that we can offer to our customers so that they don't have to really spend some time in building this ecosystem, right? We really want our customers to build stuff for their customers, for their end users. We don't want them to like spend time on the undifferentiated heavy lifting part, right? That's the key part of AWS, is trying to eliminate all those undifferentiated heavy lifting from our customers so they can focus on the key business value that they bring to their customers. So what did we do with this? So let's talk as a simple example of how VR implementation is typically done, right? This is a use case that I'm working with my customer around AWS Wavelength and helping them onboard their application into Wavelength and make sure that they understand the benefits of what 5G is bringing to the table and Wavelength is bringing to the table, and also learn from the customer, right? This is a journey for all of us to understand how and what impact that edge computing can bring to the table along with 5G. So typically, if you look at a VR implementation, most of the time, because of its very strict latency and throughput requirement, it is all done in-house, like tethered or untethered, right? There is a massive amount of GPU or a big GPU farm is being invested by the customer to build applications, to test application, and to deploy applications and to test them, right? It's all in-house. They have GPU instance types or machines with high-end GPUs running connected or tethered or untethered, and then they deploy their applications and they test it, right? On-prem, there are a lot of use cases, right? Retail use cases, oil and natural gas industry is actually looking at a lot of them are looking at a VR for collaborative training, for connected engineer use cases. You name it, every use case, every vertical has some sort of requirement on VR application, right? Impact of VR is going to be on every different use cases. So this is how it has been done. Video data is being generated by the head mount devices, is being processed by the local GPU compute, and it handles perfectly well. We all know that, right? But how can we make a change to this? Because the mass adoption is not going to happen if this embedded requirement of GPU is there for VR. And that's where CloudXR, as I told you in the previous slide, CloudXR and other ecosystem is going to help move the needle towards mass adoption of how can I disaggregate the head mount device and GPU so that these GPUs can these applications can benefit from the cloud model, right? I have seen some customers use the public CloudXR option where they run their VR engine, they run their VR applications in the cloud, and they get connected through public internet. There are very, very few use cases that can actually run. In fact, there are some customers who actually showcased how they can even pull this off using some intelligence that is added on top of CloudXR engine and other VR engine that they've built, so that they can kind of adapt to the changes to the network, right? Some applications, because of its requirement, can run in a public cloud environment, but not most VR applications with the strict requirement on latency and throughput might not actually work well in a region, as well as where you disaggregate the compute in the region as well as the head mount device in the on-prem location. So again, highly dependent on the use case, highly dependent on where the locations are and how well you're connected back to the region. If you have a direct connect to the region, certainly you can pull this off because direct connect gives you that dedicated bandwidth and low latency connectivity to the region. So that's possible. But the mass adoption, right? We're talking about mass adoption and bringing that cloud model to the VR use cases. This is what Wavelength brings to the table, where we're bringing that AWS compute closer to the edge of the mobile network, so customers can deploy their AR, VR workload inside Wavelength zone computes using a G4 instance. We support G4, which comes with the Tesla T4 GPU. Because of that, you're getting the best of both the worlds, right? You're getting the GPU that you needed to deploy your VR application. You're getting that low latency from a 5G network and the throughput, and you don't really have to worry about deploying your GPU on-prem or even connecting that to the region using direct connect and other mechanism to get you that low latency. So this gives you a fascinating opportunity for you to go and test your VR application and see how things can operate in a 5G network. Let's move on to an actual use case itself, right? It's pretty much the same type of a reference architecture. It's a remote connector, remote engineer use case where customers are looking at how I can improve the safety of my workers by means of using VR applications. That's exactly the same topology, exactly the same way we are bringing Wavelength and helping customers to solve their VR needs by bringing compute closer to the edge with 5G rolling out across different parts of the country, especially in a remotely connected areas where network reachability of network is pretty hard. With 5G going into places where connectivity challenges are removed, even with 4G sometimes, we can certainly think of connecting edge computing, connecting AWS Wavelength and G4, running CloudXR Stack on your G4 instances or any other VR stack to see how you can increase the adoption of VR for your end user applications. If you are in this field and you're starting to test and research in this area, this is a fascinating opportunity for us to start testing and learn from what the network can really provide and what the edge computing like Wavelength can provide for VR adoption. All right, so what did we do in the lab, right? So we have a 5G lab where we basically connected the device through a hotspot, Wi-Fi hotspot. You can ask me a question of why did you use a hotspot? But because unfortunately there is not a commercially available device which has 5G integrated in the head mount device. So we had to go with this choice of hotspot, Wi-Fi hotspot with a 5G router, and then connect that to an ultra wideband, right? 5G comes in different flavors, right? There's a nationwide 5G. There is 5G which runs on mid band. There's a 5G that runs on high band, which is ultra wideband in the Verizon world, and then connect that side of the network to the wavelength zone using the ultra wideband network. As I said in the previous slides, how the packet flows, it goes through the mobile network, the packet core, and then finally it hits the wavelength zone. That's how we actually tested it. And obviously the wavelength zone is connected back to the parent region using service link, right? So this is our setup when we tested CloudXR using 5G ultra wideband. This is the best of the best you can get as far as connectivity is concerned in a 5G network. Ultra wideband, which gives you the lowest latency possible today, and high throughput, downstream download speed of close to 2 gigabits per second, upload speed of close to even 100 to 200 megabits per second. That's constantly improving. Constantly carriers are improving their 5G network to bring more and more throughput in the upstream side and the downstream side. So we picked the best architecture to test and understand how CloudXR behaves when you provide a 5G network which has the best connectivity as well as the best throughput, right? How does it behave? What are the things that we learned, and how can we continuously improve? That's the remaining part of this discussion. So we have a CloudXR client that is running in an Oculus Quest 2, and then we have an NVIDIA CloudXR server running in a G4 instance in the wavelength zone, and they're connected using 5G, right? That path is such a critical path where your control signals are flowing, your video assets are flowing, your audio signals are flowing, and the end user experience from a client perspective is so much dependent on how that green block uh, is working, right? If the green block has packet drops, it has latency, it has jitter, it is going to immensely affect the performance of the end user experience, especially in this case of VR end user experience. If you're going to lose packets, if your latency is increased because of the network performance, you're not going to have that great an experience when you're doing some VR applications, right? So it has to be so important to get this right for customers to really be confident that they can certainly take this and understand how they want to deploy this in the network and take it to the masses. What we also did is, as we did more and more of testing in the lab, we quickly ran into a challenge where there's a lot of logs that is created, right? A lot of logs that is created by the CloudXR stack, especially the 2.0 with latency profiler built into XR 2.0. You will see there's ton of QoS logs, trace logs is being collected at the client side as well as on the server side. So it becomes such a manual effort for us to really parse these logs, understand what's happening. Is there a certain configuration that I have to pass in to this client side or the server side, or I have to make sure that the 5G network is configured a little differently? So many things has to be configured properly to make sure that you have a better end user experience. So a lot of logs is created, and it becomes very cumbersome to parse these logs for every test you're doing. So what we did is we said, let's actually use Amazon Kinesis for using some backend automated logging purposes, right? So we have a Kinesis agent that is running in the server and on the client side, so that we can automatically stream these logs to the backend, and you can do all kind of processing and analytics at the edge, right? Once you have the data in the AWS cloud, I don't even have to say what are the tools that you have to do dashboarding, to do ML algorithm on those logs, and really understand how things are actually doing. In fact, we are thinking of extending, by means of working with our carriers as well as other ISV providers, if there is any other levels of logs that we can send for a session, so that we can stitch the session together and see what is happening. It will be very, very immensely useful for our ISV partners, as well as any end user who wants to really test and validate it. So there is certainly an undifferentiated heavy lifting over there, which we are trying to solve for our customers, so that it makes it easier for them to focus on the VR application deployment, as well as executing that for their customers. Again, as I said, from the server side as well as the client side. Okay, let's quickly look at the logical flow. The reason why I want to touch upon this is because there is a challenge when you run CloudXR in the wavelength zone, right? There's a simple challenge that we ran into it, and we addressed it for our customers, right? So technically speaking, when a client wants to connect to the server, it establishes a RTSP session using 480.10.0 or 480.10. It describes, it sets up, it announces, and does a play, right? It's pretty straightforward. It has nothing to do with what wavelength zone is, or client or server combination, right? It's very generic RTSP type of communication that happens between client and server, not just CloudXR client and server. Any client and server which wants to establish a video session, they can use RTSP protocol for exchanging SDP parameters, and then they can send video and audio across these two endpoints, right? So then a video UDP flow starts for video, audio, and control, which is very important, right? Because you're establishing that video flow so that you can start to send H.264 feed to your end devices from the server side, so that it can render those images. And also there's a control flow back from the head mount devices back to the server, so it can act accordingly based on the user movement and things like that, which is pretty simple and straightforward, right? The challenge is, if you really look at the traffic flow, there are several layers of NAT that happens, right? There is a carrier IP, which is associated to a wavelength zone EC2 instance. There is a carrier grade NAT that happens inside the mobile packet core. Then there is a 5G gateway, which is the 5G router, which sits in the client side. They all have their own IP. So there are several layers of NAT that happens. Again, it's very straightforward and simple and similar to any type of video application that run in a network between client and the server. The reason why I'm talking about that is there is a concept called NAT punch through that the server does, so that the packets can flow through these NAT gateways. The UDP flow can actually go through these NAT gateways without any disruption for those sessions, because these are dynamically set up sessions. The punch through has to happen for the UDP packet to flow through, and only then these packets can actually reach the client as well as the server. Without that punch through, the UDP packets are dropped by the NAT gateway. So there is this function called stun server, right, where you can use the stun to discover your own public IP. So there is a stun query that goes from the server side, and there's a stun query that goes from the client side to discover their own public IP, so that they can use this for doing that NAT punch through process. Again, this works fine. The only challenge here is, since we don't support UDP ingress, the NAT binding request, the stun binding query that goes out to the Google stun server doesn't come back in the wavelength zone. So when you try to establish a session, a CloudXR session, you might see that your session will fail because of the lack of stun response that is coming back. I have seen the CloudXR server kind of intelligently work around that by means of using the SDP parameters, and also and understanding the IP addresses where these RTP sessions is originating from. It can certainly do the punch through even if the stun binding query fails, but it takes a long time, almost like 30 seconds before your session is established, which is a long time, right? You're like opening up the client, trying to connect to the server, and you're waiting for 60 seconds with a head mount device connected to your head, and you're like waiting for the sessions to establish, not knowing what's happening, right? We don't want our customers to go through their experience. That's the reason why I'm talking about this, where in the wavelength zone, it doesn't happen in a region. If you deploy your CloudXR in the region, it doesn't happen. But in the wavelength zone, because we don't allow UDP ingress come in back, or ingress traffic to come in if it's not established inside, especially UDP packets or connectionless, we don't allow UDP response. The binding response from the stun server doesn't come back, right? So how do you solve it? What we did was we actually deploy a stun server, like for proof of concepts, where every customer can use that stun server to overcome that need for going out to the external server and doing a query, right? This is a kind of a simple hack, but again, it's making sure that our customer don't run into challenges and waste their time in terms of troubleshooting this problem. So I am highlighting this. Once that stun is local, you do a resolution across that stun server, binding resolution, and then you're good to go. And that's how the cloud server and the client connects, and you get that UDP flow created, and then you start to see the experience of how well 5G performs, how well a 4G network performs, what's the differences and things like that. So keep that in mind. The stun server has to be local, and we can actually help you out if you're starting to deploy inside the wavelength zone. All right, so let's quickly touch upon the results, what I've seen, right? As you know, round trip time is so critical, right? The frames that is being rendered has to be as fast as possible. In fact, if you look at a 70 frames per second or a 90 frames per second and you do the calculation, there's going to be 17, 16, 15, 14. There is a round trip time millisecond has to be so lower in the sub 10 milliseconds sometimes for certain games because of the way the games are being rendered. So latency becomes such a key factor, right? The network that we tested gave us a round trip time of close to 19 milliseconds. And am I saying this is the best? Certainly not, right? There are other parameters that evolves. Is there quality of service there? Is there packet drop that happened? What happened in the network? So there's a lot of things that is happening underneath the covers, which the customers have to really know. And that's where these results will help the customer to have a baseline when they get started. So the latency was 19 milliseconds. One thing I want to highlight, when you compare these numbers to the setup that we did, remember there was not native 5G connectivity from a head mount device. So there is always this Wi-Fi latency translation from 8.2 to 11 into Wi-Fi into NG RAN. That takes almost 3 to 4 milliseconds. So you can certainly see, as more vendors or more head mount devices come with 5G, native 5G connectivity, you're certainly going to shred off at least 3 to 4 milliseconds out of this. That's the maximum, that's the best you get? Certainly not, right? You can get better and better and better as more and more carriers are provided that they're building these new 5G networks and more spectrum is available and more connectivity options comes in. You're going to see, obviously, there are other aspects of 5G networks that I'll talk about a little bit in the final closing slide. What makes it more and more interesting that we are in a 5G will become more and more real and more possible for customers to deploy, right? So latency becomes such a key factor. So keep that in mind. And where did I get all these results from? I did not measure it on the network, actually. These results are all coming from NVIDIA's latency profiler, right? So the application is telling us this is the latency it is seeing, right? Not just sending some probes here and there. It is the application itself is sending, the server telling us, the client telling us from the application side. So these are real good numbers to look at to really understand how the network is behaving from an application standpoint, right? At the end of the day, application has to see the network and use the network to the fullest, especially for VR applications where the requirements are pretty strict. Frames per second. What is the effective frames per second we got in our testing is 71.2 frames per second. The device Oculus Quest that I have doesn't support 90 frames per second. So that could be the reason, or maybe the network didn't afford to actually do beyond 70 frames per second. We're still digging in with that results, right? So you have a better device, right, which supports 90 frames per second. You go into the lab, do the testing with the same infrastructure. Do we get 90 frames per second? We might, right? So those are some of the things we have to constantly test and understand from these results. why I'm not getting 90 and why I'm getting 85 may be a difference, right? Is this because of packet drop? It's because of latency, or because of jitter, because of number of hops, or because of the server side GPU capabilities? So many factors can affect the end-to-end performance. And this is why these results are very interesting to review with the customers, as well as to help them kind of get settled and start deploying their VR applications. Jitter, a massive factor for how the stack will see, or how the server and the client kind of negotiates in terms of what profile that they want to connect with, and then the server is going to render and encode the frames accordingly. So jitter is another factor. In our testing, we saw an 890 microsecond of average jitter. Client queue delay is another factor, right? How long that the client is de-jittering for the frames to be given to the decoding buffer, right? This is another factor that NVIDIA told us it's very important to look at when you're testing a CloudXR stack. So this number is a very important. As low a number is so good for the user experience. Frame time in XR, right? The frame time in XR is another explanation that is given as part of the documentation. If you go and look at the SDK docs of CloudXR, like the time it takes for a user movement to be captured and encoded and ready to be decoded, right? So the round trip time delay, along with the encoding aspect on the server side for picking up a right image and encoding it, and then sending out the frames to the client before the client is ready to send it to the decoding buffer. So that's the time that frame time in XR means. And what this time is also should be lower as possible, so that your actions are translated into rendering as quickly as possible, right? So this is again another key number, or another key aspect to really look at when you're doing the testing. All these numbers come from the client side of the stack. There are also numbers on the server side of the stack, which is where aggregating the server side logs and the client side logs for a specific VR session is so important to understand as you make changes on the network side, on the client side, or the SDK side. Lots of cool combinations you can do and test it out. And finally, so next steps, right? We are working very closely, right, with so many different ISV partners and our end customers. So making their life easier, removing their undifferentiated heavy lifting for them to get started. We are building CloudFormation template. Kudos to the AWS Spatial team, which actually built the initial CloudFormation template. William built it, who's an awesome SA, part of the Cloud Spatial template Spatial team. I extended that CloudFormation template to use Wavelength as well. And then we are adding more variables into the CloudFormation template, where you don't have to worry about the stunt server, and all these Wavelength specific stuff is being added into the CloudFormation template, right? Like creating the carrier gateway, carrier IP, setting up the EC2 instance. So leveraging the initial template that William from the spatial computing team built, and extending that so that our customers can go start right by means of running the template. They are ready to go in terms of testing CloudXR in the Wavelength zone. Centralized logging is another one. I will tell you for sure, this will become such an important aspect as you start more and more testing, because there's going to be tons of logs that is piling up on the server and the client side, and you have to really concatenate that. One of the idea is to see how we can add logs from the network itself to combine them together to give you an end-to-end view of how your application is performing. Continue testing with the head mount device with native 5G, right? We have a couple of partners, unfortunately I cannot name them, who are working on an integrated head mount device with the 5G. So as that device is available for us to test, we'll go back and continue to test, eliminating the need for hotspot with Wi-Fi. A standalone network, right? 5G as of stands today, there is two versions of 5G is implemented. It's a non-standalone network and a standalone network. There's not much of standalone in the commercial network as of this point. It's only in the testing in the labs. Once standalone network is available, it's actually going to improve dramatically the backend performance, right, of 5G. So what does mean to me, like a VR developer, the latency is going to go down, the throughput is going to increase when the standalone networks are available. And one more important aspect of that, of standalone, is network slicing, right? Network slicing is such an important piece for VR use cases, where the application can ask for a certain bandwidth and throughput and the jitter performance from the network for their session. So think about it. When you're ready to go and start a VR session, you send an API, and ask for a network slice before you start the session. So your requirement in terms of latency and throughput is reserved for you in terms of a slice, right? That's the highest level. There's so much more to network slicing, but I'm just giving an example. So when standalone networks are available, when network slicing is available, even in the lab, we'll actually go and continue to test and share the results with our customers so that they know what to expect when they're ready to test CloudXR and other VR applications in the wavelength zone. And finally, private 5G networks is another game changer, right? A lot of enterprises and a lot of smart factory use cases are dependent on private networks. They're building their private 5G networks. Think about all the use cases in a factory floor and an industry floor or in a retail industry where VR can actually make a positive impact for the business goals. So we are also going to validate and test, is there anything we can do as far as VR adoption is concerned, not just in a commercial network, but also in a private 5G network with various levels of quality of service and other aspect of providing that level of differentiation for VR applications. So those are the next steps. We will come back with more results. We will share more results in blogs and other webinars. So if you have any questions, please reach out to us, to the Wavelength team on these aliases and URLs. If you want to start getting access to Wavelength zones, it is opt-in only for now. You can actually go to that link, the sign-up link, where you can get access to the Wavelength zone and get started with your VR journey. With that, thank you so much for your time today. Hope it was useful. And if you have any questions, I'm happy to take it now. Thank you.